Let's take a look at lab 9.1, which is going to be called a ripple counter and the character displays. So in module 9, what we have started looking at is modeling sequential logic with a process. And a process allows you to trigger a signal assignment based upon another signal transition or another event that is not the signal that will be assigned to or signals that are assigning to the output. Okay? Said another way, you can have other signals trigger the process. That allows you to model things such as a D flip-flop. And we looked at the model for a D flip-flop in that it triggers based on a clock or a reset, but what it does when it triggers is it makes an assignment to the output Q. Now, if the reset is asserted, you set Q to 0. That's what reset means. And that's the highest priority signal. And it's asynchronous, meaning that no matter what the clock's doing, no matter what the inputs are doing, you reset it. If you're out of reset, then you look for a rising edge of clock, and every time you see a rising edge of a clock, you make the assignment from D to Q. That was the model for a D flip-flop. Now, D flip-flops are used in everything, but one of the neat things about a D flip-flop is you can build a very simple circuit called a ripple counter. Okay? And so if you remember what a ripple counter is, let me show you the schematic for a ripple counter. Let's see here. So if you remember what a ripple counter is you basically take a D flip-flop and you take the inverted output called Q bar and you feed it back into the input D. What that does is it puts it into what we call a toggle flop configuration. Every time you get a rising edge of a clock, the output will toggle between a 0 and a 1. And the way that you think about this is if you reset the device, the output Q is a 0. Well, the inverted output Qn is a 1. And so as you start seeing edges of clock, what will happen is that if the output inverted, Qn, is a 1, it is the next value that will be latched into Q. So the first time you see a clock edge, Q will go to a 1 from a 0. So now Q is a 1, the inverted output is a 0, that 0 is fed back and it will be the next value to be latched in when you get a rising edge of a clock. And if you do this over and over and over, all that Q will do is toggle back and forth between a 1 and a 0, 1 and a 0, 1 and a 0. The cool thing about it, though, is that the frequency at which it toggles is 1/2 of the frequency of the incoming clock. When you think about a binary counter, bit 0 is running at some frequency. It's a square wave at some frequency. Let's say a kilohertz, or let's say 1,000 hertz. Bit 1, the next highest significant bit, is going to be running also as a square wave, but its frequency is actually half. Okay? So when you line those two signals up together, bit 1 is half the frequency of bit 0. And if you look at bit 2, it's going to be half the frequency of bit 1. And bit 3 is half the frequency of bit 2. And so if you have the ability to divide a square wave exactly in 2 with regards to its frequency, you can actually start building up a binary counter. And that's what a ripple counter is. So a ripple counter is where you take a D flip-flop and you put it in a toggle flop configuration. In order to get the phases to align, what you do is you clock the next stage, the next toggle flop, with the inverted output, okay, of the previous stage. So if you take a bunch of D flip-flops and you wire them in this way, and the clock comes in only to the first bit, only into the first D flip-flop, this output on the first D flip-flop will be the fastest moving bit, or we could call it bit 0 of a counter. The next output of the subsequent D flip-flop will be running at half the frequency, and that we could call bit 1 of a binary counter. And if you cascade all these together, and they're all clocked by the previous stage, you will actually get a nice binary counter. And what's great about it is you don't use any combinational logic whatsoever. All you do is use D flip-flops. What's even cooler than that is that as of chapter 8 and 9, you know how to model a D flip-flop using a process. Okay? So here's what your lab is going to be for 9.1. Let me go to the beginning here. And here's what we're going to do. Okay? We're going to build a big ol' ripple counter. Okay? Now, What we'd want to do, though, is we want to see the ripple counter. We want to see the binary counter. The issue is that the input clock on the DE0 nano board, or the DE0CV, is actually running really, really fast. Okay? And if you come down and you look at the DE0 board, okay, you will see that it actually has a crystal on it, and it provides a 50 megahertz clock. Okay? So if you use that to drive a ripple counter, what's going to happen is that bit 0 will be toggling at what frequency? It'll actually be half of the incoming clock, so it'll be 25 megahertz. That's still 25 million transitions, or 25 million periods per second. That's too fast to see. But bit 1 will be moving at only 12.5 megahertz. Is that too fast to see? Still too fast to see. Then the next bit will be moving at 6.25 megahertz. Is that too fast to see? Too fast to see. So we keep adding D flip-flops to divide down the previous bit frequency until we get to a frequency that we can see with the human eye. So one question becomes, how fast can the human eye see? Think about a TV refresh rate. When you go purchase a TV, what are the refresh rates that you see on the box? 60 hertz, 120 hertz. Okay, so we need to see things that are measured in hertz. Even a kilohertz is blazing. So we can really only see things that are like a hertz is 1001, 1002. 2 hertz is 1001, 1002, 1003. 10 hertz is like tick, 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 tick. You can still see it, but it is getting very fast. So what we need to do is find a way to observe the counter at a frequency that we can see. Really what we need to do is just keep adding bits to the counter until the most significant bits are slow enough so that they're at a frequency that we can see with the human eye. It turns out that if you calculate it down, we need about 38 bits to be able to slow this thing down slow enough so that you can see the bits on an LED. Okay? So what we're going to do in this lab is we're going to take the upper 10 bits of the ripple counter, so these are the most significant bits of this 38-bit ripple counter, and we're going to drive the red LEDs on the DE0CV board. Okay? Now, we have not used all of the LEDs yet, so you have to actually, in your top.VHD, you have to go in and expand your LEDR port to go from being 0 to 3 from up to 0 to 9. That means you're also going to need to do the pin assignments for that. You're either using a CSV file or doing it manually using Pin Planner. Now, what we could do though is our character displays. You guys have already created a component called car decoder. It takes in 4 bits and it outputs a hex symbol that drives one of these hex displays. What we want to do is that will allow us to take 4, 8, 12, 16, 20, 24. We can actually look at 24 of the bits of the counter if we display them through your car decoders. So what you're going to do is take the upper 24 bits of the counter and drive these character displays. Now, having said that, you're going to be able to display those upper 24 bits as 6 hex characters. So this is kind of neat, 6 hex symbols. The lower ones are still going to be super fast. I mean, they're going to be blazing, okay? You're still not going to be able to see this, but you will be able to see the slowest one or the most significant 4 bits of your counter. If you look at the block diagram of what we're going to do, it's pretty simple. You are going to come into your top.VHD, and what I'd like you to do is build a D flip-flop as a separate file. Okay, so you're going to build a new file called dflipflop.vhd. It should follow all the practices that we've covered so far. So it's going to be done using the standard logic 1164 package. It's going to have ports that are of type standard logic. It is going to use a process with a rising edge clock triggered device or behavior and an asynchronous active low reset. Okay? This is the same D flip-flop that is directly out of the textbook, so it shouldn't be difficult to do this. But I want you to create this dflipflop.vhd file, and then you're going to instantiate it in your top.vhd. If each of the D flip-flops will hold one of the bits of the counter, how many D flip-flops will you need to instantiate? 38 D flip-flops. That's not a big deal at all. There's 100,000 plus D flip-flops on the FPGA, so it's not a big deal to instantiate 38 of them, okay? What is a trick, though, is keeping track of all the nets, because you're going to have a whole bunch of wires going every which way. What you're going to want to do is create an internal vector called count, and I would recommend making one called count n, and those will be then used as your internal wiring to wire the ripple counter up. So if you go look at the ripple counter again, you're going to need all sorts of wires. Every D flip-flop will need a wire that will be routed back from its QN output to its input D on every single one of them. So if you made a vector, which is called count n, you could use each of those bits to do the routing. You could also create another vector called count, and that will be wired to the Q output of all the D flip-flops. That will hold your counter vector, okay, the 38-bit counter. What's neat about it is that you can then just simply do signal assignments from that 38-bit vector to wherever you want to go. For example, if you come into here, you are going to create a port for your top.vhd, which is called LEDR. And it's going to be 9 down to 0. It's going to be 10 bits wide. All you got to do is make an assignment to that from the upper 10 bits of your count vector. So it would simply be LEDR gets assigned, and then count 37 down to, what is it? Something, 28 or something like that, okay? It's a very simple assignment. Then what you can do is you can pluck off 4 bits at a time of the count vector, and you can run it into your car decoders. How many car decoders are you going to need in this? You're going to need to instantiate 6 of your character decoders that you've already done. Okay? So when you look at the top.vhd, you are going to have 38 instantiations of your D flip-flop. You are going to have 7 instantiations of your car decoder, and you are starting to move into the way that digital systems are designed. You build a component and reuse it over and over and over. And we're just going to keep doing this over and over as our labs get more and more complex. Very straightforward for that part. Okay? How's this feeling? All right. Where's the clock come from? Well, I just showed you a picture. There's actually a 50 megahertz crystal on the board. It is going to produce a nice 50 megahertz clock, and it comes into a pin on the FPGA. The reset, where are you going to get a reset? Wouldn't it be nice to have a button that you could press, and it would pull a reset line down to 0, reset everybody, and then when you let go of it, it will come out of reset? Well, it turns out that there is a button that is wired directly to the FPGA, and if you look at what it's called on the DE0 board, it's called FPGA reset. So the designers of this FPGA board knew that you wanted this, so they put this in there. It is normally outputting a 1, and if you press that button, it will pull the line down to a 0. The output of this switch circuit is wired directly to the FPGA. So all you got to do is find the pin assignment and bring that in and call it the reset line of your top.vhd. Okay? Same thing with the clock. You got to go find where the pin comes in here, and then you're good to go. Okay, so life is good. One other thing that would be cool is to monitor some of the other bits that are running at the fast rate. Okay? So with LEDs and character displays, you have to slow them down. But wouldn't it be cool to see the top 8 bits? Wouldn't it be cool to see the ones that are counting at 25 megahertz? You're clocking the thing at 50 megahertz, and I want to see the fastest 8 bits. We haven't seen them yet. Well, we are going to use the Analog Discovery 2, which is a portable lab instrument that allows you to take logic analyzer measurements. It also allows you to do things like be an oscilloscope, output digital logic, voltmeter, power supply, all that sort of stuff. But we are going to hook this up, and we are going to take a measurement on the lower 8 bits of the counter. And in order to do that, we need to route them over to someplace on the FPGA board that we can see those signals. So if you look at the picture of it, this DE0CV board has these things called general purpose I/O pin headers, and they're called GPIO_0, GPIO_1, and they're all connected to the FPGA. So anytime you want to see a signal in your design, in your VHDL, you just create a port, and you route the signal you want over to that port, and do the pin assignments to these pins. You bring this analog discovery guy out. It's got little female connectors that plug onto the pins of this pin header, and you just pop it on there, and then you just configure the analog discovery to acquire that information, and you can display it as an 8-bit bus. Okay? So that's what we're going to do. So that's the final thing when you look at this block diagram. You have a clock coming in. You have a button coming in, and nothing else is coming in. On the FPGA, you will create a 38-bit counter in a ripple counter architecture. You will do that by creating a D flip-flop and instantiating it 38 times. You will reuse your card decoder 6 times to drive the character displays. You will then route 10 of the upper bits of the counter over to the red LEDs, so you can see those. And then you're going to have this new port called GPIO_1, which is going to have the fastest 8 bits of your counter. The analog discovery will be connected right here. Okay? All right. So when you think about this lab, what I do here is, again, copy last lab. You have a lot of the pin assignments already done. You don't want to start from scratch. What you're doing, though, is expanding the ports. If you look at the entity definition for lab 9.1, let's take a look at it. You now have a clock. You now have a reset. You have a switch. You know what? We're not even using the switches, are we, in this lab? Leave them there, though. You're going to use them at some point. Doesn't hurt anything if you don't use it. Okay? Just leave them in there. Leave the pin assignments for it. Quartus will take care of ignoring it. How about LEDR? Notice that we had to expand it up to 10 bits. And then we had our hex 0 to hex 5. We already have those in there. But here's a new guy. GPIO_1, and it's going to be 8 bits. Okay? So you pop these in there, you do all the VHDL design, you're going to take a nice video of this counting, very small video, 2 megabits, okay, and 2 megabytes, no 50 megabytes, 50 megabytes bad, 2 megabytes good, okay, so we're working toward figuring out how to make these videos very small, and then you're going to upload what? You have a logic analyzer measurement. Okay? If you've never used the analog discovery, what I do is I walk you through every step as if you never have. So you're going to have these analog discoveries that are sitting next to the DE0CV board, and you're going to wire them up. You're going to launch a tool called Waveforms. That's the display for the analog discovery, and I walk you through how you set it up. You're going to add the signals, you're going to configure them, and in the end, this is going to be what you're going to see on the analog discovery. You're going to be able to look at those 8 bits as a bus. You're going to look at them as, you can put them in decimal if you want. How high does a 8-bit counter count to in decimal? Yes. The answer is yes. So 1 bit goes to 2, 2 bits goes to 4, and it goes 8, it goes 16, it goes 32, it goes 64, 128, 256. Okay? So you have 256 unique symbols. It actually just goes from decimal 0 to 255, then it starts over again. So you should be able to see all that. You can also view the counter in its binary form, which will actually show you the ups and downs here, and you should be able to measure and see that it is actually running at 25 megabits. Okay? So this whole lab sets you up and walks you through that. But the deliverable for the second deliverable is a screenshot of your analog discovery measurement. Okay? How's that feel? Third deliverable is your top.vhd. So there's actually 3 things you're going to upload. You're going to upload your demo video, you're going to upload your analog discovery screenshot, and you're going to upload your top.vhd. Okay? And that will be lab 9.1.